I want to continue our lecture on perturbation theory applied to non-degenerate state. Okay, our last lecture, we stopped until evaluating the first order energy corrections. The first order energy corrections to the approximate energy. To calculate the ground state energy. The first order energy corrections. The first order energy corrections is given by this formula containing the perturbations and the zero order or the unperturbed with functions or orbitals. So we can evaluate this. Okay, I will leave this as an exercise in tutorial. This inter-electronics repulsions potentials R1, 2 here can be written explicitly in terms of spherical harmonics. So L is the angular momentum quantum number. So M here is from negative L to positive L. Okay. We continue from here to here. To L plus 1. And R here, power of L. Okay. This notations, okay, means R here is smaller than the R1 and R2. And R, L, 1, and this notation mean is larger than of R1 and R2. Okay, times the sphericals harmonic. So this complex conjugates and times this spherical harmonic. Theta 1 and okay. So theta 1 and pi 1 here is the coordinate for the electron 1, and theta 2 and phi 2 here is the coordinate for electron 2. Okay. To evaluate these integrals, we can use these expansions of R12 here in terms of spherical harmonic. So this is the spherical harmonic you learn in mathematics asas or in physical 1, physical 2. One can show that, okay, we can write this R1 over R12 here, okay, in terms of this spherical harmonic. So substituting this expansion of R12 into these equations, you can see this depends on this angle theta and phi. So R12 R here, this is R2 and R1. So for this R, the symbol means, okay, this R radius smaller than R1 and R2, and this means larger than the R1 and R2. So this we divided by this one. Okay, so we can evaluate this one, this fraction. So I will leave this, okay, in tutorials. So once we evaluated these are the first order energy corrections, we can find this approximate energy. Okay, we are here considering only the first order energy corrections. So the zero order, of course, can be obtained. Okay, I want to recap this. Are zero order or the isotopes or the hydrogen-like energy for electron 1 and the hydrogen-like energy for electron 2. Okay, which is, okay, which this energy can be obtained from the exact solution of the hydrogen-like Schrodinger equations or the unperturbed Schrodinger equations. Okay, so these two are the ideal energy, okay, from the exact solution of Schrodinger equations. So we use, okay, these informations from the unperturbed system to approximate our energy. Okay, so this is the approximated energy. We use these informations from the unperturbed system, okay, to get this E. So you can compare this with the experimentals, established experimentals data with this error 5.3. percent. Okay, how we get this error? Okay, 9.01. Okay. Okay, so we can determine this percent error in our calculations. So now we want to look the perturbation theory for a degenerate energy levels. Let's say we have these several energy states, okay? For the unperturbed system, for the perturbed system, and we can vary this parameter lambda. This lambda appear, okay?
Doctor, sorry for interruption.
Sorry?
Someone need your permission to enter.
Oh, okay. What? Huh. Okay, can I allow students to accept other student entering this what call uh, this room or this group? Is there any button here I can set so that you can also allow your friends, okay, to enter here? Do you know how to set it?
I think cannot, Doctor.
Oh, only the admin only can accept the student, allow the student. Oh, okay, I see. Okay. So now we have this perturbation, the zero order. So this perturbation H prime, and when we fully turn on the perturbation here, okay, when we set this lambda here to be 1, and there is no perturbation when we set this lambda to be 0. Okay. So these hypothetical models, okay, for these general variations of lambda, we can see the energy here. Let's say when we turn off this perturbation, okay, so the E4 will be at this levels, E2 will be at these levels, E4 and E5, and E1 and E3 here, E1, E2, E3 here, okay, they are degenerate energy levels, and this is 6. If you have here a mixture of non-degenerate energy, E4, E5, E6, okay, plus this E1, E2, and E3. When we turn off this perturbation, we can get this something like this. So when we turn off this perturbation gradually from 0 to 1, what we can see here, the degenerates energy here split into 3 different energies. If the first order energy corrections, they are all different. Okay. If this first order energy correction here for E1 here differ than this E2, okay, what I mean this one. So we can have here 0 order plus E1. So this E0 plus E2 and this E1. E0, the 0 order energy, plus E3. First order connection. If this E11, E12, and E13, they are different, so the energy will split into 3 different energy. Okay. If they are still the same, so the first order energy correction is not enough, okay, to split all these degenerate energy levels. Maybe we need higher energy corrections. For example, the second order or the third order, okay, or higher order energy corrections in order this energy degenerate energy split. Okay, you will see this later on how we can split this energy, okay, when the first order energy corrections, okay, is not able to split this degenerate, where we can use this second order. The second order here, okay, you will see this like the coupling between spin and orbital angular momentums, the spin orbit energy. When we consider the coupling of spin and the angular momentums, the spin and orbital angular momentums, the spin and orbital angular momenta, so the energy will split. Okay. So this higher order spin orbit energy, you will learn this, and maybe this energy, we can make it this energy into different energy. If this energy is not enough to split this energy, when we apply an external fields, whether the magnetic fields or electric field, okay, which is the third order energy corrections. So when we apply this external magnetic field, basically the first order energy corrections when we consider this inter-electronics potential energy repulsions between electrons. So this is the first order correction here, means the interaction between electrons. So now, let's say we have here this unperturbed Schrodinger equations for unperturbed systems, where we can solve this. Okay, Schrodinger equation, we can solve this exactly this Schrodinger equation, and this known Schrodinger equation, in fact, you learn in physical 1 and physical 2. The simplest, a few simple system. Okay, the non-interacting particles in one-dimensional box, an electron in hydrogen-like atoms, and so on. So, for examples, the hydrogen-like atoms, the energy here, okay, probably the energy for 2px, 2py, or the 2pz. Okay, and they are the same. They are here, this energy in atomic unit. Okay, so you learn this is the energy. So the n here depends on the n quantum number here, 2. Okay. For helium, we have 2 protons, Z is 2. Okay, the orbitals. This is the orbitals. Sorry. Oh, sorry, I can write it like this. So this is the wave functions, which means this is 2 the linear combinations of these complex hydrogen-like functions. Okay, this will give equivalent to 2px. Yeah. Or you can write as, okay, like this. X, sorry. So this is the orbitals, okay, what you can get from the solution, exact solution of this Schrodinger equation. And we have here the perturbed system with its perturbed Schrodinger equations. Now we include more electrons. Here we have only one single electron here, so we can now perturb this system with inclusion of this second electrons due to this energy repulsions, potential energy repulsion. So the Schrodinger equation here is no longer solvable. So we cannot solve this one. Okay. We want to use, to solve this one, we want to use all the information here. Okay. from these solvable Schrodinger equations. Okay. You can see this one. Okay, let's say we set this lambda to be 0. Lambda to be 0. So if lambda to be 0 here, when here lambda here approaches to 0, the energy here also will approach to this energy, the 0, or the energy. Okay. In this course, what you learn in physical 1, physical 2, this E will be here denoted as 0 order. Right? So this is 0 order. What you learn in physical 3. To differentiate with this unperturbed energy, or the unperturbed, the perturbed energy and the perturbed wave functions. Okay, we want to differentiate this. We use these notations. So when this lambda here goes to 0, of course this energy goes to this energy. So they are all degenerate, like this one. It's all degenerate. Let's say we have 3 different energies here. EP, E2px, E2py, E2pz. So this goes to this energy, the 0 order energy, or the unperturbed energy here. Okay. How about these wave functions? Okay. We cannot write simply like this one. When limit here, this lambda goes to 0, we can confirm get this wave function as the 0 order wave functions or the unperturbed wave functions. Okay, so we cannot here confirm to get this one. Because of what? Because the wave function here, when this energy lambda here goes to 0, it could be a linear combination of these wave functions. Also, an eigenvalue for this energy. Okay. The eigenvalue for this energy. The linear combination of this. Let's say you have 2px, 2py. So this is 2. And this one is 2pz. The linear combination of this px, py also an eigenfunctions of this energy state. Also one of the solution of the Schrodinger equations. Let's say like this. Also an eigenfunction. So we generalize this. Okay. When lambda here goes to 0, the perturbed wave function here goes to the linear combination of the 0 order. The 0 order here, like in these examples, okay, is given by this one, this formula. Okay, so this is the 0 order. So we can write here, actually we have corrected this with when this lambda goes to 0. Okay, we corrected the 0 order wave function here. So we can write here, so the correct 0 order wave functions when we apply the first order energy perturbations. At the same time, we will get the corrected 0 order wave functions, which is the linear combinations of 0 order wave functions. This the correct 0 order wave functions. Okay, this formula, okay, you will see how we apply this to the helium's first excited state. So it becomes more clear how we can use these definitions of the correct 0 order wave functions when we consider the first order perturbation theory. Okay. Now we want to find what is this psi and what is this E, the perturbed energy and the perturbed wave functions. Okay. We want to relate this perturbed wave function and perturbed energy with this one, unperturbed wave function and the unperturbed energy. Okay, how we are going to relate this using this one? Okay, we want to use all the information here, okay, from this equation. Okay, so we know this. Okay, one, and we know this one. Now we want to expand this wave function and the energy in terms of Taylor series, as what we done for the non-degenerate perturbation theory. We can here expand these wave functions and this energy in terms of Taylor series. So now we can write it like this. Okay, expand through the expansion of this wave function in terms of Taylor series. So we can expand this and we will consider up to the first order energy corrections. Okay, so the difference here is only this one. Okay, comparing this with the degenerate perturbation theory, the 0 order, when the lambda goes to 0, we can confirm that for the non-degenerate perturbation theory, we can confirm this. Okay, when lambda here goes to 0, we can confirm that we can get this 0 order. For the non-degenerate energy levels. One wave function here, this energy, okay, state, the wave functions represent only by one wave functions, this energy state okay, this energy state is represented by only one wave function. This energy state one wave function, this energy state is one wave function. So when this lambda, okay, when goes to 0, we can confirm get these wave functions, okay, goes to the unperturbed wave functions. Like, for examples, 1s is the unperturbed or the zero order wave functions. This is the ground state. One energy, one wave function. So this for the non-degenerate perturbation theory. So we can write like this. You can refer, okay, this. And compare to the with this formula, this one. So this is the first order corrections. Okay. We want to compare this with this one. The zero order, of course, we know this energy goes to the unperturbed, okay, or the zero order energy. So okay, the difference only on these first terms, okay, for this approximate energy, which is the linear combinations of zero order. Okay, instead of this one, we can confirm get this zero order. For the degenerate perturbation theory, the zero order here actually is the linear combination of the zero order. So this is the corrected versions of the zero order. So we want to look what is this psi 1 here, the first order energy corrections, and sorry, not this one, this one. We want to look this one only, not this one, and this energy. Okay, and this already known, this value. Okay. The problem here is the first order energy correction. When we apply the perturbation theory, at the same time we have here corrected the zero order. We function here. This is the zero order. So the first order energy corrections and the correct zero order. The correct zero order mean here. Okay, so this is the correct zero order. And the first order here. This one. 0. And also the manipulations to prove this one. Okay. To obtain the first order energy corrections, okay, is quite lengthy. It takes few pages to prove this. And the solutions for for this energy correction, first order energy corrections, is given by this linear homogeneous equations. Again, we have seen this in linear trial functions, linear homogeneous equation with this unknown coefficient C, 1, C2, and CD here. Because the correct zero order wave function here, okay, is from I1 to D. So this is the coefficients we are looking for here, this coefficient C. So we have here D degenerate state, E01 up to E0D degenerate state. We want to use the perturbation theory. Okay, this is without interactions between particles. Okay, for instance, in helium between two electrons. So we have here degenerate state, degenerate state, energy state. So we have here D energy, the number of energy here. The energy here. And each of these state, okay, has its own wave functions to characterize this state and this as well, for examples, and so on. So the summation here goes to here from 1 to D. So we have here D degenerate state with same energy here, having same energy, but with different wave functions, depending on here on different orientations of these non-interacting particles as non-interacting particles. So we want to look this E. What is this E? So we can write in this short form of the linear homogeneous equation here by writing like this one. So this expression here, okay, is for these linear homogeneous equations. So we can expand this from 1 to D here. Okay, this means row, this means columns in matrix form. Okay, you can see here the summation here is from 1 to D. So this is from 1 to D. This is columns, the first columns, the second columns, and this is the D columns. Okay, this one is for the row. M1, M2. So this is 1, 2, and D. So we'll get here these simultaneous equation, homogeneous equations with these unknowns C, D unknowns of C. Okay, so the linear combination of this zero order will give the relative contributions when the energy, okay, split when we apply perturbations, the linear combination of each of these zero order wave functions. So again, if we have this linear homogeneous equation, D linear equation, what is the solution of this linear homogeneous equations? Again, we have here two kinds of solution, the trivial and the non-trivials. The trivial one, when we set all these coefficients here to be zero, when we set all here to be zero, of course, if see all here to be zero, and this will be zero. So this is not the solution we want to consider here. Okay. We have this second kind of solution, okay, which is called this non-trivial solution. The circular equations for these D coefficients here is zero. So the coefficient here, okay, this one, C1, C2, and so on here. So the circular equations for this C unknown here, the coefficient here to be zero. The circular equation here to be zero. Okay. So now we have here, if you have here D simultaneous equation, we will get here D by D circular equations with this D roots of first order energy corrections. So we'll get here these D roots energy equation. For instance, let's say we have two degenerate state, okay, with this one zero order. We can form the solutions, okay, for the first order energy correction is two simultaneous equations with the C. The solution of these two simultaneous equation is 2 by 2 circular determinants. And the 2 by 2 circular determinants will get two roots of first order energy corrections. 1 and 2. So this is first order energy corrections. Okay, solving this circular equation, we get these two roots. Now we can substitute one of this root, let's say this one, into this equation. We substitute into here, we substitute into here, and we substitute into here. When we substitute into here, this E, we can get this C1, C2, all these coefficients. For examples, in this case, for 2 doubly degenerate state, this one 2 doubly degenerate state, we substitute this E1 into these two simultaneous equations. We solve these two simultaneous equations. We can get one of two set of C. C1 and C2. Once we know the C1 and C2, of course, we can get this form. C1 C2. Sorry, this is 0. Okay. Okay, once we know this one. And then we can substitute this E, the second E, the second root into these two simultaneous equation. We get this second set of C1 and C2. Once again, you can write this C1 prime 0 order plus C2 prime. This is psi 1. Okay. So now this energy, if the E here, E1 and E2, let's say this E1 and E2, E2 here larger than here till larger than this E1. So the energy here will split into this energy. Oh. So this is E0 plus E1. So this is E0 plus the E1 2. Okay, if they are different here, this E, because of the first order equation. And each of these state, okay, described by this, the zero, the correct zero order wave function here. So this is the corrected one, and this is the corrected one. Now, okay, we want to apply this to particle in three-dimensional box. We know the first excited state energy for a particle in one-dimensional box, they are degenerate. This is the triply degenerate state. The lowest state here is 111, correct? This NX, you learn in physical 1. The quantum number here for this X, Y, and Z. When we said here this is the lowest quantum number for particle in three-dimensional box. Three combination of quantum numbers here. So this is the first excited state. Energy, but with different orientation here. Okay, for example, the contour plot will be something like this. Okay. This is only one. If we look, okay, at one side of this, okay, so something like this, okay, this one, the contour plot, so this is something like this. So now, okay, when we have here this triply here degenerate state, three false degenerate state, we can split this into three different energy. Okay, provided that we have different E here. The first excited state was this particle in a cubic box. Okay, for this, let's say we put two particles here. So the interaction between these two particles will generate this E1 here. We perturb this system with this interaction between two particles. Okay. So now the energy here, when we consider these interactions, the energy here, we solving these secular determinants. So this in Dirac notations, okay, 211, all possible combination here of a quantum number here. So this is 211. This is 211. Okay, so this is 121. This notation. Okay, for Hamiltonian's matrix element, this notation, the Hamiltonian matrix element. So this is 211 or 211, for example. So this is the Hamiltonian matrix elements. The integrals here. So this is integral. So now you can see here these examples. Okay, how about we have only one energy state? Of course, we'll get this only one homogeneous equations. This one. If you have here one energy state, this non-degenerate state, what we need to solve here is only one linear homogeneous equation. So if one linear homogeneous equation C1 equals 0, so we can determine this E1. Which is H prime. And this one is the zero order one, the perturbation, this matrix element. Okay, of course, this is the complex conjugate. This is zero order, and this is one, d tau. So this formula what we got from here, okay, from the non-degenerate perturbation theory. For the one energy state, let's say this one, we will get this one linear homogeneous equation and one by one secular determinants. Okay, where we can get this one. We get back this one. Okay, for the non-degenerates perturbation theory. Okay, this one for the non-degenerate perturbation theory. So now we want to see here the real applications for first excited state of helium. Now for the ground state, we have seen this in our previous lecture. occupying this 1s state, 2 electron here occupied in 1s state. Now we are going to promotes one electron here up to here to s. Whether you here promoting this one electron to 2s or 2px or 2pz, 2py or 2pz, will still get this same zero order energy. Because of what? In atomic unit, okay, I'm writing here in atomic unit for electron 1, for electron 2, sum of these two hydrogen-like energy for electron 1 and electron 2. So n here only depends on this quantum number, principal quantum number 2. Or 1 here, this 1. Okay, so if this is electron 1 in this lower state, so n is 1. If electron 2 in 2s or 2py or 2pz or 2px, so n here is 2. If electron 2 here in 1s, electron 1 in 2s, electron 1 or in 2px or in 2py or in 2pz, so this is what we get. 1, 2, 2, 1, you still get the same energy here. Okay, now we have we still here didn't take here into account the electron interactions. So the zero order, we use this zero order. So electron 1 here could be in 1s, electron 2 could be in 2s, electron 1 could be in 2s, electron 2 could be in 1s, electron 1 could be in 1s, electron 2 could be in 2px, electron 1 could be in 2px. You can continue. You can get 8 possible combinations of these 2 electrons lying in 2 different states. And we have this state 4 doubly here degenerate state, 1 this non-degenerate state. So we'll get here 8 different combinations here. So this is zero order, still zero order. Okay, if you want to plot this, okay, if you can understand these energy levels, so actually you have understood all this entire chapter. So this 8 degenerates energy levels, the zero order or the unperturbed. Okay, so this is all here. Okay, we have here these 8 possible zero order with functions having same energy here. Okay. Now we are going to use the first order perturbation theory when we consider the electron interactions. When we consider these electron interactions, okay, the next steps in our calculations when we consider the electron interaction. When we consider the electron interactions, okay, eventually we need to solve these 8 by 8 circular equations. Because of what? Because this is the solutions of 8 simultaneous linear homogeneous equations with these 8 unknowns of coefficients C. We have here 8 simultaneous equation, 6, 7, 8 simultaneous equation with C unknowns coefficients. These 8 unknowns coefficients. These 8 simultaneous equations. Okay, I will discuss this next week using the parity considerations. We can prove all these off-diagonal matrix, they are zero, leaving only this block diagonal matrix. We have here 4 block diagonal matrix. Okay, this is how we define. We have seen this. This one, we define this one. So this is H1, 1 prime, E1. So this is Hamiltonian's matrix elements in Dirac notations. Okay. This H prime, the perturbation, which is the interelectronic repulsions. This Hamiltonian matrix element. So we can reduce this, the 8 by 8, which is the non-trivial solution of this 8 simultaneous equation, to this block diagonals for diagonals matrix. So this is diagonal block, this is block diagonal matrix. Okay, I will explain this next week, how we can get using the parity, odd and even functions for 2s and 2p. We can prove this, the integrals inside this matrix element will be zero. Okay, one of this block, you learn in mathematics asas, we have 4 blocks here. Okay, you should know the solution of each of these. We can write, okay, simply like this. Equals 0. So the first block here, A, you can set here to be 0. Now, okay, this is one of the block. Let's say the first block A. Okay, we have what we call this 8 unknowns coefficient C, right, from the solution of 8 simultaneous linear homogeneous equations. So the correct zero order wave function here okay, will be from 1 to 8. This is 1 to 8. 1 to 8 here, you have seen this. 1, 2, 3, 4, okay, to 8. Zero order wave functions. Once we consider the interactions, we correct the approximate energy with the first order energy correction. At the same time, we correct the zero order wave function. This is the uncorrected one. We want to correct this, which is the linear combination of this. Okay, this is one of the corrected zero order wave functions where these three we have here up to C8. But we have proof, okay, from here. The C3 contribution here, C4 here, C5, C6, the matrix element here, inside here, they are 0. We only have here C1 and C2. Okay. So this is all are 0. So we have only C1 and C2. Next, for the pi 1, we have this second set of C1 and C2. This one, okay, for this block. We want to solve this block. So this block is 2 by 2 matrix, right? So this what we'll get. Sorry. This one. Okay. And C1 and C2. C1 bar, C2 bar. Okay, I want to stop this lecture until here. And then we will continue next week.